Before I begin today's lecture, I would like to remind you of certain things. In this country, there is a very big misunderstanding, or rather a misconception, I would say. The misconception is that optimization as a subject, which is actually a part of mathematics, or if you want to be slightly more politically correct or incorrect, whichever it is part of applied mathematics, we equate it to, or we rather say optimization is same as operations research. But this is far from truth, because usually in many places operations research courses teach largely linear programming, which is minimization of a linear function over a polyhedral convex set. Of course, I have not told you anything about polyhedrality or anything like that yet, and there is a course on convex optimization which is already live on YouTube given by me. You can go and look at that course to have an idea about what are convex sets and functions and linear optimization and linear programming. Now, the question is this. So, people equate operations research with optimization, and there is a growing tendency among mathematicians in our country to say that okay, this is a part of operations research which is largely done at business schools. So, optimization cannot be a part of mathematics. What the business school guys forget that operations research is not just optimization. Optimization tools are applied in operations research. So, optimization problems appear in operations research, and many of the areas, many problems can be solved by optimization techniques in OR. For example, there is optimization modeling here in OR. There is, for example, inventory control, there is scheduling, there is queuing theory. So, there are many aspects of operations research. For example, Markov decision processes can be also taken as a part of operations research. So, these are the tools which people in business need, business school need. It is not the tools which every other thing needs. For example, a problem in physics would need to be bothered about inventory control. So, optimization is a subject which is feeding these problems in business or operations research. Okay, it is pretty good to teach operations research at business school, while our mathematicians forget, especially in this country, that optimization is a very ancient subject. There are many geometrical problems of maxima and minima which we had started in the very beginning, and optimization, for example, in its fold has mathematical programming, which is finite dimensional optimization, which is actually applied to this place. Also has in its fold a very important ongoing chapter in mathematics, the calculus of variations, which is infinite dimensional optimization, and its modern version for more complicated problems is optimal control. Not to say our other issues. So, these are highly mathematical subjects, this and this. So, optimization is a subject in mathematics which is helping other subjects. So, calculus of variations, for example, is used in engineering and other natural sciences. This is used in engineering, operations research, natural sciences. Engineering and natural sciences. Optimal control problems are even used in biology. but they are mathematically very involved topic, not only a beautiful part of mathematics, but a very lovely and interesting part of mathematics. So, optimization is actually a very vast thing, one hand helping operations research and on the other hand helping other sciences, and being centrally a mathematical issue, centrally a subject with mathematics of breathtaking beauty. So, it is my request to those who do mathematics and want to divide as pure and applied mathematics, please note that subjects like calculus of variation or optimal control is a part of optimization. If you consider, I do not know at all whether you would, is a course, is a part of mathematics, because one has to understand a lot of function analysis had come in because one had needed to answer or solve problems in the calculus of variations. So, lot of types of function spaces etc. had come up because of the requirement of calculus of variations. So, calculus of variations, just like ordinary optimization in those days, had fed a lot of things into mathematics, and had led to a lot of mathematical development. So, if you at all consider calculus of variations and optimal control as subjects of mathematics, optimization, which is the mother subject which contains all these subjects, cannot be a subject which is not a part of mathematics, as mostly said. And the number of people teaching optimization in maths department in India is dwindling, and possibly across the world in many places, and optimization is now largely done in business schools, unlike the US universities. The people who teach from the business school here largely are not maintaining the rigor that you need to teach optimization, the mathematical rigor, because they are just told that this is a tool that you have to apply, it has got nothing more to it, and hence the mathematical beauty of the subject is lost. Okay. Now, giving this very basic and important fact, I also now want to make sure and tell very clearly that what or whom I am expecting to be a listener to this course. I do not expect a first year engineering students to listen to this course. The engineering student should be at least in his third or fourth year to listen to this course, and a mathematics student should be at least in his master's degree first year to listen to this course, because it will be mathematically involved, and as we go along the mathematical involvement would be more. Of course, we would not at all go to infinite dimensional spaces, we will try to avoid the issues of non-differentiability as much as possible, but still keeping into that level of elementariness, you would say. Still, I would request people who are not mathematically inclined not to get into the details of this course. Of course, you can just skim through and just see what is been told, but a lot of proofs etc. would be done. For example, now we will start talking about the Fritz-John conditions or the John conditions, and from here we will go along. Now, let me start with a problem which you study in calculus. In calculus, when you study function of two variables, you are usually asked to look at a problem like this, where you minimize a function of two variables, two real variables x and y, subject to another function in satisfying h x y equal to 0. So, basically take all those x y's which satisfy this, and among those x y's find the one which minimizes this function. Now, the problem is that how do I go about it, and if I am just given this problem, how do I start to visualize an approach to the solution. Now, the whole idea is that we have some information about unconstrained minimization, which is a much more simpler thing. The question is, here I have constraints. So, how would I go about dealing with the constraints? Now, in order to do so, what I would do, is to replace the constraint somehow and make the problem unconstrained. So, idea is make an constraint problem unconstrained. So, how do I make it? Suppose I am able to solve this equation h x y is equal to 0 and I now can write y as a function of x. So, from here I solve h x y equal to 0 and I can write explicitly h x y equal to 0, I write explicitly and I get y as a function of x. Basically, I should write y equal to y x, but okay, just. So, there is an explicit relation between y and x. Once I know the explicit relation between y and x, then of course, I can put in, I can replace y here with, and now I can just minimize over R, it becomes an unconstrained minimization problem in R. So, this is an equivalent problem. So, the equivalent minimization problem is this. So, if I can always do that, then why I need to bother about so much certain things which you have heard called the Lagrange multiplier rule. Now, if you look at this, what I will do next is to, if the function is differentiable, I will take a derivative and equate it to 0. But you have also heard about this thing called Lagrange multiplier rule, where what you did in your calculus course was to add the, just take some lambda as if it is coming from the air, and you added the constraint to the objective and formed a new constraint, a new objective which is now unconstrained. And then your job was to take the derivative first with respect to x and with respect to alpha, that is find an h x y. So, here you will get 3 equations, 1, 2 for two partial derivatives and here 1 equation. So, here you have 1, 2 real numbers and third. So, there are 3 variables and you have 3 equations and you can solve it. So, you say okay, hence I solve it, but nobody asks the question why you do this. This lambda is called the Lagrange multiplier. And this is called the Lagrange multiplier rule. Now, can you make arbitrary rules in mathematics? That is, just say okay, if I want to do this, just add something to something and just take gradient equal to 0 and you will get the solution. How do I know that the thing that I will get from here can be considered as a candidate for solution? But unfortunately, in our calculus classes we never question this, at least in India. I have never seen people questioning this fact, that how do I know if I do that I will actually get a candidate which can be even suspected of being a solution to this problem, to that problem. This has also got something to do with our mathematical education and the way we take science, because here we are really discouraged to ask questions. It is from my own childhood experience also, my own student experience. you are discouraged to ask questions. You are just a listener who listens to whatever has been told, and you have to be reproducing in the exam whatever has been told to you. But any sensible person with a sense of mathematics would ask that I know that if I have a function from R to R, or even say Rn to R, does not matter, and if you say that x star is a local minima, local minima or local minimizer, it gives you the local minimum, then it implies that, so any local minima must satisfy this equation. So you know that whenever if I have a point x star which satisfies this could possibly a candidate for local minimum. So whatever Lagrange has done like this, in this way, and we just mug up these things, we possibly do not ask ourselves a question. So if x bar and y bar is a local minima to this problem P, say, what is the necessary condition? What sort of condition does a local minima to P satisfy? Lagrange did not provide a proof that if you do by this, that any local minima would actually satisfy a thing like this. If you are using to find a local minima, at least a candidate point whom you can suspect as a local minima, then what you should do is that you should be able to find a lambda in R such that this is true. Find a lambda in R. So your job would be to find lambda in R such that this is true. Now Lagrange did not prove this, it was proved much later in the 20th century. Now that is the whole point. People do not ask, people do not realize that this is a necessary condition. If x bar y bar is a local minimum, then under certain condition, for example here I would have grad of h x y not equal to 0, if that happens, then what I have written here is true. Then x bar y bar would necessarily follow this set of equations, and hence if you calculate x bar y bar from here, you can suspect it to be a candidate for solution. But here what we do in our calculus courses, we said okay, whatever you get x bar y bar you get, basically you will get the lambda also as a byproduct, which you think is okay, just somehow it has come unnecessary evil. But then if you just get the x bar y bar, you say okay, this is the solution. We still do not realize that optimization is not such a simple thing that you take to do get something from the necessary condition and say that this is a solution. It is only a candidate for solution, you can suspect it to be a solution, but you really have to guarantee that it is a minimizer, local or global or whatever. So if you want to guarantee, you need some other conditions whose satisfaction would lead to the fact that x bar y bar is indeed that critical point which satisfies this is indeed a minima, and that is the second order conditions on which we will touch a little bit at the end, but not at the end as we go along for the study of the Fridtjohn and Karush-Kuhntacker conditions. So now this rule is called the Lagrange multiplier rule, but this is actually a necessary condition. You under certain condition that if you take this fact that grad of h x bar y bar is not a 0 vector, then this condition will hold true. So here suppose I can write y is equal to phi x, then what I am able to do, I am able to do this, I am eliminating y and replacing it by x as function of x, and then I am minimizing over x. So I am eliminating and differentiating. The standard procedure is elimination followed by differentiation. But what Lagrange said was something different. He said first differentiation and then elimination. Differentiation followed by elimination. So, it is a reverse procedure, but if I can always eliminate and then differentiate, I will prefer this, I do not want to get into all this. But the problem is that you cannot always get this explicit expression. So, you cannot always have the elimination, but you can get an explicit expression locally, and that comes by using the implicit function theorem. So, what you can get is, if hxy equal to 0 and the Jacobian matrix is non-singular, then y is phi of x locally. Locally means there are certain points near x bar y bar. So, if x bar y bar is a solution to this, so around there will be a certain points around x bar y bar, suppose this, sorry I made a mistake. So, if this is equal to 0, then there will be certain points around x bar y bar, the solution. So, if this is satisfied, so in a small neighborhood of x bar y bar, for all pair of points x y, there will be this explicit relation. Of course, y bar would also be phi x bar. So, this idea is called the implicit function theorem. We will not get into the details of implicit function theorem, nor will we apply it, we will do the proof in a different way. Lagrange applied his method successfully to huge amount of problems in the calculus of variations. So, there is a standard set of problems in the calculus of variations called the Lagrange problem in calculus of variations, and one of the most interesting papers in this direction is due to G. A. Bliss. It is called the Lagrange problem in the calculus of variations. And it appeared in the American Journal of Mathematics in 1930. I just American Journal of Math 1932, I guess, if I am not mistaken. It is a very old paper, but it shows to what extent and how successfully in the calculus of variations Lagrange has applied this method, and that is how it became famous as the Lagrange's multiplier rule. So, that's all. Now, let us come back to the 20th century, and the 20th century inequalities started entering the picture of constraints. They were not equalities only, and that inequalities became the hallmark of many engineering applications, and this sort of entrance of inequality started with the linear programming problem, which many of you might have even studied, but not to the extent that we would like to. But so, a general form of a optimization problem became of this form: minimize f(x) subject to gix less than equal to 0 Okay, please remember when I have spoken about this implicit function theorem, we are all expecting very nice behavior from these guys, means I am expecting this to be continuously differentiable and all those things. On to P and X element of capital X. So, F Gi and Hj, each of them are functions from Rn to R, and X is a closed set in Rn. Now, this is of course the objective function which you have already known. This is the set of inequality constraints, there are m of them. This is the equality constraint and this is the additional called the abstract constraint. For example, in many cases you will be given the scenario where x would be lying between say ai, xi would be lying between ai and bi. So, xi would be lying between bi and ai, the closed interval for every I. So, the whole x is now lying in the Cartesian product of these intervals, and this set is nothing but your x in most cases, many cases, but not in every case. So, this is the general form of the mathematical programming problem or the finite dimensional optimization problem, which we will henceforth refer as MP. The question is, will a Lagrange multiplier type rule or approach hold for MP? So, that is the question which was faced by the people interested in optimization in the second half of the early second half of this of the 20th century, because the utility of linear programming was becoming very clear during the war, and hence linear programming means these all functions are linear or affine. We will discuss it in detail later on as what sort of problems can be modeled into this general form. Now, the question was this: will a Lagrange multiplier rule hold for MP, and if, under what conditions and what are the issues? If I assume that all of them are continuously differentiable, will such a rule hold, and how can I use the multiplier, how can I handle this and all those things. Now, just having a closed set is not always a feasible one. What we will have is a closed and convex set. We have just spoken about convex sets, but we have not gone into much detail. So, we will have a closed and convex set, because you can observe here we have taken a convex set. Now, we have simplified the problem slightly and said, okay, if this is my scenario, of course, you can take x equal to Rn also. What I am going to get, what sort of Lagrange multiplier rule I am going to get. And here there is an interesting piece of history of nonlinear programming or just optimization theory, which we need to tell you, that would be interesting to you. Going back to the history, this all record in the 1950s and late 40s. Linear programming, where there is the same problem, but with x of course of this sort of form, and maybe x just greater than equal to 0, x is in Rn plus, x is capital X is Rn plus, and if f is a linear function, gi is our affine functions and hi is our affine functions, and okay, that is all, and x is in Rn plus. That was a sort of thing that was done in linear programming, because let me just write down a standard linear programming problem, that is, say you want to minimize a linear function, any linear function is given as an inner product in a finite dimensional space. That is the Rees theorem, and you can just prove it automatically. Very, very simple to prove this. And once you know this, so now we have to have constraints. Once this is a linear function subject to certain inequality equality constraint. So I can have ai x minus bi, which are affine functions less than equal to 0, I is from 1 to m. I can have say vectors di x minus ci is equal to 0, what not ci, sorry, I just change the notation. CI's are already here. PI minus QI, 0, sorry, PJ minus QJ, J is equal to 1 to P, and you have all the x 1 x to xn. So, all of this whole thing can be collectively written as so the problem is to minimize Cx over these two constants and x is in Rn plus, and that is called the linear programming problem, LPP. So, it is like a problem of that form. In 1951, there was a seminal paper published in the Proceedings of the Symposium of Mathematical Statistics at which was held at the University of California at Berkeley, and there the authors were Harold Kuhn and Albert W. Tucker. So, both were from Princeton, Harold Kuhn being the student and Albert W. Tucker being the PhD supervisor, and Albert W. Tucker was a PhD supervisor also of the now famous John Forbush Nash. And of course, those who have seen Beautiful Mind possibly won't realize they have shown both Tucker and also Kuhn, because the friend of a very close friend of Nash was being shown in the movie, and he was Kuhn, and Albert W. Tucker was the teacher who started the person who started talking about the movie, talking in the very first scene. He represented Albert W. Tucker. So, they published this paper in 1951, where they published some sort of a Lagrangian multiplier rule for this class of problems where everything was continuously differentiable. But what they did not do, so let us see. So, the problem they considered that was a problem which was devoid of equality constraints. So, they said okay, we will be really bothered about the equality, we will not bother about the equality constraint, Lagrange has already bothered about it, we will just bother about inequality constraints. And took all these functions f and gi from Rn to R to be convex. And they proved that under certain conditions, which is called the Kuhn-Tucker constraint qualification, under certain conditions on these constraints, so under Kuhn-Tucker constraint qualification, they showed that there exists, these are all differentiable functions, convex and differentiable, that there exists lambda 1, lambda m with lambda 1 greater than equal to 0, lambda 2 greater than equal to 0 and lambda m greater than equal to 0, such that, so just relook at it, and of course it is characterizing a minimum. So, if x bar is a local is a minimum, so because it is a convex problem there will be no local minimum, which we will talk about later on. If x bar is a minimum, then under Kuntaker constant qualification there exists this such that so you see there is a sign on this constraints, it does not free like the lambda here, just in lambda in R or here there are only one constant, just for sake of explanation. So, the number of multipliers is same as the number of constraints, and you see here the multipliers have a sign. Number 2, a very important notion called the complementary slackness condition. He said they have said this will happen if the functions are convex, but they also said if x bar is feasible. So, if it is a convex programming problem, we will call it CP. So, if x bar is feasible and there exists lambda 1 greater than 0, lambda 2 such that 1 and 2 hold, then x bar is a global minimum, is a global minimum of CP. So, x bar is a global, so that is what they proved. So, this became famous, this whole story, this whole result became famous as the Kuhn-Tucker condition. Now, the important thing is that this result, which is true for convex case, now you see this Kuhn-Tucker constant qualification is useful, we are not telling what is that. When you are proving that if x bar is a solution of this problem, then this will hold, it is only for the necessary part this is all right, it is required, but for the sufficient part then you do not need to bother about this, you need to know that whether this is just having a solution and whether you can solve this system of equations. This result became famous as Kuhn-Tucker conditions, and the optimizers was very happy because somebody finally gave them an analog of the Lagrangian multiplier rule when inequality would come. And it, for a convex case, it was both necessary and sufficient. They actually were going from linear to convex, convex differentiable and so on. Now, they had proved for the linear case without any additional constant qualification, means additional assumption on the constraints, you could prove a rule like this. Of course, only with the inequality case, not the equality case. Now, it was later on found that Karush, who was in the group of the Chicago group of optimization led by Magnus or Hestenes, he had in his master's thesis, W. Karush had written about this sort of multiplier rules, but in a very different context for a very special problem. So, nowadays it is known as, from 80s I think, it is known as the Karush-Kuhn-Tucker conditions or the KKT conditions. but the real story of the Lagrangian multiplier rule for this problem, where we both have inequalities and equalities, was not told by Kuhn-Tucker. Unfortunately, most books in optimization do not try, unless written by very good optimizers, to highlight the role of one of the most unsung heroes of optimization theory, and his name is Fritz John. He was a very specialist in partial differential equation and did this single contribution to optimization theory, which really tells you about the general nature of the Lagrange multiplier type rule for this problem. We are having equality and equality, and he published his findings, his result way back in 1948, and nobody knew it when this Kuhn-Tucker conditions came. Kuhn-Tucker conditions is just an easy corollary of what Fritz John had done, is much more general. He first sent this paper to Duke Journal of Mathematics and they rejected it. Later on he published in some obscure proceedings, but he, for example, is unfortunately the unsung hero of mathematical programming and optimization theory. People just do not talk about the conditions which John has given, but here in this talk we want to give this person his due, and we would start discussing what is the John multiplier rule. So, the KKT condition is, as we will show, a easy corollary of this the John multiplier rule. Essentially the John multiplier rule is what we need and nothing much more. So, and that is actually the Lagrange multiplier rule for this sort of problems consisting of both equalities and inequalities. So, with this let me stay, and in the next class we will first take just this problem without convexity thing and take the John's approach and see what happens, and then we will add the equality and then take John's approach and see what happens. Thank you very much for your attention.